Hello everyone, welcome back to ChemPoetry, your chemistry companion. In today's class, we are going to discuss a very important topic from Mass Spectrometry, Ionization Techniques. If you are preparing for your PG semester examination, NET GATE, university examination or Viva, this topic is very important because ionization is the first and one of the most essential step of mass spectrometry. In this class, we will understand what is ionization, why ionization necessary, characteristics of an ideal ionization method, hard and soft ionization, electron ionization or EI, fragmentation in EI, chemical ionization CI, mechanism of CI, methane, isobutane and ammonia as a reagent gas, and finally classification of different ionization techniques. So let's start. First, let us understand the basic idea. Mass spectrometry is an analytical technique used to determine the mass to charge ratio or M/Z of ions. But there is an important problem. Most molecules present in our sample are electrically neutral. A mass spectrometer cannot measure a neutral molecule. Therefore, the first step is to convert these neutral molecule into ions, and this process is called ionization. So remember this simple sequence: neutral molecule, after that the ionization process, then ions are separated according to the M/Z ratio, then detected. Today our main focus is that the first step is ionization. What is ionization? Now, what exactly in ionization? Ionization is the process by which a neutral molecule is converted into a charged species by gaining or losing electrons or by other charge transfer process. For example, in electron ionization, M plus E minus gives rise to M positive radical plus 2 electron. Here M represents a neutral molecule. When it loses an electron, it forms a positively charged molecular ion. The dot indicates that there is an unpaired electron, so this is called a radical cation. Why is ionization important? Because it is the first step in mass spectrometry and it produces the ions that can subsequently be separated and detected. So, without ionization, conventional mass spectrometry analysis cannot proceed. Now, the question is, why exactly do we need ionization? There are four major reasons. First, it converts neutral molecule into ions. Then, charged particles can be controlled and moved using electric and magnetic fields. The mass spectrometer measures the mass to charge ratio M/Z. And the fourth one is the ion and their fragmentation patterns provide information about the molecular mass and molecular structure. So, the key point for examination is a mass spectrometer analyzes charged species, not neutral molecules. Therefore, ionization is essential. Now, let us discuss what an ideal ionization technique should provide. An ideal ionization method should have high ion production. We want sufficient ions to obtain a strong signal. Second, the stable ion. The ion should survive long enough to reach the analyzer and detector. Third one is good reproducibility. If we analyze the same sample repeatedly, we should obtain similar results. Ideally, the molecular ion should remain intact with molecule weight information is important. And finally, it should be applicable to a wide range of compounds. So, now we come to a comparisons. Hard ionization versus soft ionization. The easiest way to remember the difference is hard ionization equal to high energy plus more fragmentation. Soft ionization equal to low energy plus less fragmentation. In hard ionization, sufficient energy is transferred to the molecule. Therefore, the molecule can break into many fragments. These fragments are extremely useful for obtaining structural information. The example is electron ionization. On the other hand, in soft ionization, less internal energy is deposited into the molecule. Therefore, fragmentation is much less. The molecular ion or related molecular species is usually much more prominent. This is particularly useful for determining molecular mass. So, remember this exam trick. Hard equal to breaks more, soft equal to stay more. EI is generally considered a hard ionization technique, whereas CI is a soft ionization technique. Now, let's discuss one of the most important ionization technique, which is called electron ionization. Electron ionization is a hard ionization technique in which a beam of high energy electrons interacts with gaseous molecule to produce ion. Typically, electrons of approximately 7 electron volt are used. The basic reaction is M plus E negative gives rise to M positive radical plus 2 electron. The molecule M loses an electron and form a molecular radical cation. This molecular ion can then undergo fragmentation. The important compounds of an EI source include electron source, filament, ionization chamber, sample inlet, ion extraction system. The sample must generally be introduced in the gas phase. The result is a molecular ion plus several fragment ions. The fragmentation pattern acts almost like a fingerprint of the molecule. That's why EI spectra are extremely useful for structural identification. Let's now understand the working step by step. Sample vaporization. In this step, the sample is converted into the gas phase. After that, electron emission. A heated filament, commonly a tungsten filament, emits electron. Then electron acceleration. These electrons are declared to high energy, typically around 70 electron volt. After that, the fourth process is collision, and in this process, the high energy electrons collide with gaseous molecule. And step 5 is ion formation. The collision removes an electron from the molecule and produces a molecular ion. Then the fragmentation is the sixth and last step. Because the molecular ion contains excess internal energy, it may break into smaller fragment ions. These ions are then extracted and sent toward the mass analyzer. This sequence is very important for your examination, like vaporization, after that electron emission, acceleration, collision, ionization, fragmentation, and analysis. Now let's understand why fragmentation occurs in electron ionization. When a molecule receives high energy from the electron beam, the molecular ion becomes energetically excited. It can therefore undergo bond cleavage. For example, take a simple molecule such as propane. C3H8 plus electron gives rise to C3H8 plus radical plus 2 electron. The molecular ion is formed. Then the molecular ion can break into smaller ions. For example, cleavage can produce fragment ion such as C2H5 plus and other species. The exact fragment depend on the molecular structure and the stability of the resulting ion. This is extremely useful. Why? Because different molecules produce different fragmentation patterns. Therefore, the EI spectrum can act as a molecular fingerprint. Important point for your examination is the molecular ion peak helps us to determine the molecular mass, while the fragment peaks help us understand molecular structure. Now, let's look at the advantage and disadvantage of electron ionization. Advantage. First, EI is relatively simple. Second, it gives highly reproducible spectra under standardized conditions. Third is, there are extensive spectral libraries available. This is a major advantage because an unknown compound can often be identified by comparing its EI spectrum with a reference library. Fourth, EI gives excellent structural information because of its characteristics fragmentation. After that, we discuss the disadvantages. The major disadvantages is extensive fragmentation. Sometimes the molecular ion peak becomes very weak or may even be absent. Therefore, determining the molecular weight can be sometimes become difficult. So, EI is not suitable for many thermally unstable or non-volatile compounds because the sample generally needs to enter the source in the gas phase. Now, we have identified a problem with EI. EI gives us excellent structural information, but it can produce excessive fragmentation. If fragmentation is too extensive, the molecular ion peak may be weak or absent, then determining the molecular weight becomes difficult. Stronger molecular ion related peaks. Chemical ionization, abbreviated as CI, is a soft ionization technique. Unlike EI, the analyte molecule is not primarily ionized by direct collision with a high energy electron. Instead, a reagent gas is fast ionized. The reagent gas ions then react with the analyte molecule. After that, common reagent gases include methane, CH4, isobutane, C4H10, ammonia, and S3. The important concept is electron fast ionize the reagent gas, then the reagent gas ion react with the analyte. As a result, the analyte often form a protonated molecule or another related ion because the analyte receives much less excess energy than in EI. Fragmentation is greatly reduced. Therefore, CI is especially useful for determining molecular mass. Let's understand the CI process more clearly. Suppose methane is used as the reagent gas. First, methane is ionized by the electrons. CH4 plus electron gives rise to CH4 plus radical plus 2 electron. Then the primary methane ion undergoes reaction and generates more useful reagent ions, particularly CH5 plus dot. For example, you can see CH4 plus radical plus CH4 gives rise to CH5 plus CH3 radical. The important reagent ion is CH5 plus. Now CH3 plus now CH5 plus react with the analyte molecule M. CH5 plus M gives rise to M plus H positive plus CH4. So the analyte gains a proton. This is called proton transfer. The resulting M plus H positive peak is often very useful for determining the molecular mass. For example, if the molecular mass of M is 100, the protonated molecules appears at approximately M by Z equal to 101. So CI gives us a very useful molecular mass related peak. Let's look more closely at methane as a reagent gas. So methane is subjected to an electron impact. Several reagent ions can be generated. The important reagents ion include CH5 plus, C2H5 plus, and C3H5 plus radical. These reagent ions then interact with the analyte. There are three important types of reaction we should remember: proton transfer, adduct formation, and charge transfer. Therefore, CI is called a soft ionization technique. Here we can see the important reagent ions generated from the methane plasma. The major ions include CH5 plus. This is the major protonating species. After that, C2H5 plus. This can participate in proton transport and related reactions. C3H5 plus. This can also contribute to reaction with analyte molecules. Their main role is to react with the analyte and generate molecular weight related ions. This is the fundamental difference between EI and CI. Mechanisms of chemical ionization. Now let's discuss the major mechanism involved in the chemical ionization. There are four important mechanisms shown here: proton transfer, adduct formation, charge transfer ionization, and proton affinity. Now let's compare some commonly used reagent gases. First is methane. Methane is widely used in chemical ionization, and its characteristics include wide application, moderate fragmentation, good sensitivity. Methane is therefore a useful general purpose CI reagent gas. However, we can obtain even softer ionization by using other reagent gases such as isobutane. Isobutane is reagent gas. Next, we can discuss. Next is isobutane. It's generally produce a softer ionization environment than methane. Therefore, fragmentation is reduced, molecular ion related peaks become stronger, and molecular weight determination becomes easier. So, if methane gives moderate softness, isobutane provides even softer chemical ionization. And one more reagent gas is particularly important, which is ammonia. Now we come to the ammonia NH3. Ammonia is one of the softest commonly used reagent gases in CI. When ammonia is ionized, it produces reagent ions that can participate in proton transfer and cluster ion formation. A key species is NH4+. This can transpose a proton to suitable analyte molecules. After that, NH4 plus M gives rise to M plus H positive plus NH3. Ammonia can also produce cluster ions because ammonia CI is very soft. It usually gives very little fragmentations, strong molecular weight related ions, good molecular mass determination. Therefore, ammonia is particularly useful when we want to preserve the molecular ion information. Because ammonia CI is very soft, it has several applications. It can be used for accurate molecular weight related measurements, differentiation of compounds that may produce similar EI fragmentation, analysis of thermally labile or polar compounds where appropriate, biochemical and pharmaceutical application. Softer ionization, after the less fragmentation, better molecular weight information. It is the general principle, but remember, the best ionization method depends on the nature of the compound and the analytical objectives. Finally, let's classify the major ionization technique used in mass spectrometry. We can broadly divide them into gas phase ionization, example electron ionization and chemical ionization. These methods generally require the analyte to be sufficient volatile or introduced into the gas phase. After the desorption ionization, this technique are particularly useful for less volatile, thermally labile, large or surface associated compound. Example included electrospray ionization ESI, atmospheric pressure chemical ionization APCI, atmospheric pressure photoionization APPI, MALD, matrix assisted laser desorption or ionization, FAB, fast atom bombardment, SIMS, secondary ion mass spectrometry, DART, direct analysis in real time, DESI desorption electrospray ionization. Each technique has its own application and advantages. For example, ESI is widely used for biomolecules and LCMS. MALD is commonly used for large biomolecules such as proteins and polymers. DART and DESI allow more direct analysis with minimal sample preparation. So ionization is not one single technique. There are many approaches designed for different type of sample. Let's quickly revise today entire class. First, ionization convert neutral molecules into ions. Second, ions are necessary because mass spectrometers measure M/Z ratio of charge species. Third, ionization methods can broadly be considered hard or soft. Electron ionization EI is a hard ionization technique. It normally uses approximately 70 electron volt electrons, produce a molecular radical cation and causes extensive fragmentation. Therefore, EI provide excellent structural information and reproducible fingerprint spectra. On the other hand, chemical ionization CI is a soft ionization technique. Here a reagent gas is ionized and common reagent gases are methane, isobutane and ammonia. The reagent ions then react with the analyte, commonly through proton transfer, producing ions such as M plus H positive with much less fragmentation. That's all for today's class on ionization technique in mass spectrometry. If you want to study this topic in more detail, the book link is given below in the description below. Do check it out if you are preparing for your PG semester examination. If this video helped you understand EICI fragmentation and reagent gas, don't forget to like, share and subscribe to ChemPoetry. Keep learning, keep questioning and keep exploring the beautiful world of chemistry. This is ChemPoetry, chemistry, poetry and the passion. Thank you so much for watching. See you in the next class.